Okay, here's a nice problem. Again, maybe a little bit of a stretch. So let's determine all values x such that the matrix A given here is invertible. So go ahead and pause the video and we'll see how this works out for you. All right, so let's go ahead and see how we're going to do this problem. Now, this matrix is invertible. There are a number of conditions that give us that A is invertible. One of them is that the columns are linearly independent. Okay. So that means that A times the first column plus B times the second column plus C times the third column equals 0 implies A equals B equals C equals 0. Sorry, I wrote this too quickly. Let's make it a little bit neater. That's a little bit too messy. Okay, this is B times 2, 5, 0. All right, now, think about how you could choose A, B, and C. All right. If x is non-zero, that means that C must be 0. Okay. Now, if C is 0, this one is gone. Now, can you find A and B that makes this sum 0? And the answer is no, because 2, 5 is not a multiple of 1, 2. So, since 1, 2, and 2, 5 are linearly independent, okay, since 1, 2, and 2, 5 are not multiples of each other, that tells me also that A equals B equals 0. Okay, so the thing is that if I have this condition, if x is not 0, right, then C must be 0, A must be 0, and B must be 0. Okay, so that tells me that if x is not 0, then A is invertible. Okay. All right. Now, what about if x is equal to 0? So on the other hand, okay. Now think about what happens when x is equal to 0. When x is equal to 0, the entire last row is 0. So, in fact, C could be anything in this combination. Not just the last row, but the last column. The last column is all zeros, so C could be anything, and A and B would be 0. So, and the has C is anything, and A equals B equals 0. So that means that the column vectors are linearly dependent if x equals 0, and that implies A is non-invertible. Okay. All right, now, since I wanted conditions, I wanted to find all x such that A is invertible, then this is my answer here. X unequal to 0 implies A is invertible. So that's my answer. Now, another way you could look at this is in terms of row reduction. I'll just talk about this. I won't write anything down. Suppose you wanted to find the inverse of this matrix using row reduction. Well, you take this matrix and you'd add the identity matrix over here and you'd start row reducing. Now, if x is 0, then what would happen? Well, then when you row reduce, this row would stay all zeros, right? Because there's no non-zero entries, you wouldn't do anything to this row. This part would row reduce to 1, 0, 0, 1, and you'd get this matrix that's not row reducing to the identity, so that would mean that A is not invertible. On the other hand, if x is non-zero, what you do is divide the last row by x and you get a 1 here, and then if you perform row reduction operations on these two, that would give you 1, 0, 0, 1. These two rows don't interact with this one because variable 1 and variable 2 are already 0, so there's no need to add any multiples of the first two rows to the third one. So if x is not 0, this would definitely row reduce to the identity. If it row reduces to the identity, it's invertible. So you get the same result, that x must be non-zero in order for this matrix to be invertible. And it's always going to be invertible as long as x is non-zero. Right, so that's the end of that one.